Hello, I'm Jonathan Cress from the University of New South Wales, and I'm going to explain how to solve one of the calculus problems from Math 1131. It's Chapter 5, Question 25, and it involves a function f, which is given by this definition here, which has a different expression for f of x when x is greater than or equal to 0 to when x is less than 0. Okay, so this is just one function f, and the definition defines it in terms of these two different looking expressions here. And the question asks us that for this function, show that it is differentiable at 0. Okay, now before I go ahead and solve this problem, and I'm going to do it in two different ways, I'd just like to explain what's going on here. So I've drawn a graph here of the function f, and the solid line represents f. So over on the right, where x is greater than or equal to 0, this red solid line is the graph of e to the 2x, and so it looks like that. I've also put a little dotted line down here in red to indicate what the graph of e to the 2x would look like if it were to extend over where x is negative. And this blue solid line here is the graph of 2x plus 1. And that's what f of x is when x is less than 0. So over here, this is f of x. And I've put another dotted line up here in blue to indicate where the graph of 2x plus 1 would extend to if it were to continue over here. And to say that f is differentiable at a particular point is to say that there is a good tangent line you can draw at that point. Okay, and we're interested in the point 0, where this sort of definition is split. And in order to have a good tangent line here, that's a nice sort of smooth join, or at least yes, we need first of all, of course, the function, the graph must join up there, meet. That's to say that the f must be continuous, because of course you know that a differentiable function, or where a function is differentiable, it must be continuous. And you can see on the picture here, it looks like it's continuous. Furthermore, in order to get a good tangent line, sensible tangent line, we need the tangent line that we would get from the red curve to match the tangent line we get from the blue curve. Okay, so now I'll go ahead and solve this using two methods. First of all, method 1, which is going to be using the definition directly. Okay, now you can look up the definition in the notes, the definition of differentiable, and I'll just write down what it is for f to be differentiable at 0. So f is differentiable at 0 if, okay, now it's differentiable at 0 if you can put a good tangent line there, and the way that that's expressed is to say that you can work out the slope that tangent line would have to have using a limit, and that limit must exist. So f is differentiable at 0 if this limit, the limit as h tends to 0 of f of 0 plus h minus f of 0 over h, if that limit exists. Okay, now the question actually doesn't ask us to find the value of the derivative, it just asks us if the derivative exists, but I'll just make a note of the fact that, of course, if this limit exists, then the number you get is the derivative. So if this exists, it's called f dashed of 0. Okay. All right, so we'd like to now try to show that this limit exists. Now, because this function f is defined differently for positive arguments or inputs to when it's got negative input, it's maybe going to be beneficial to look at the left and the right hand limits. You know that if this limit exists, then the left and the right hand limits must both exist and must agree. And so let's check those separately. Okay, I'll look at the left hand limit first. That's where h is a little bit less than 0, negative, and then we'll use this part of the definition of f. So let's have a look at the limit as h tends to 0 from below of f of 0 plus h, I'll just write as f of h minus, so f of h minus f of 0 over h. And this is the limit as h tends to 0 from below of, so what is f of h? Well, if h is approaching 0 from below, then it's a negative number, and so f of h will be given by this part of the definition here. So that's f of h is 2h plus 1, and minus f of 0. Now f of 0, when you put x equals 0 into here, you need to use the top part of the definition. So that's e to the 2, I'll write it as e to the 2 times 0. Now of course e to the 2 times 0, e to the 0 is 1, so we've got 1 minus 1. So that cancels on the top line and very quickly simplifies. So this is the limit as h tends to 0 from below of 2h over h, which is the limit as h tends to 0 from below of 2, and the limit of a constant is just that constant, so this is 2. Okay, now let's look at the right-hand limit. Okay. So the limit as h tends to 0 from the right of f of h minus f of 0 over h is equal to the limit as h tends to 0 from the right. Now we need to substitute in what f of h is in this case. So as h tends to 0 from the right, it's a positive number, and so we need this part of the definition of f. So that's e to the 2h, and f of 0 again is e to the 2 times 0 over h. Okay, now we're hoping that that's going to be equal to 2. And how can we see that? Well, there are ways to find a limit like this, but since the idea that I mentioned before is that we want to match up the derivatives from the left and the right, perhaps we can see how this really is equal to the derivative. We want to match up the derivatives from the left and the right. We can see how this really is the derivative from the right. Okay. Well, this limit here. Let's just do a little aside and see if we can see how that might be related to the derivative of the function that's defined on the right. So let's let p of x be e to the 2x. Okay. If p of x is equal to 2 to the x, then this is a differentiable function. P dashed of x is 2e to the 2x. We know that by what we know about how to differentiate the exponential function. This tells us that p dashed of 0 is 2, which is the number that we would like this to be. Okay. Okay, so let's have 0, no, sorry. We've got 2 is p dashed of 0. And what's the definition tell us that p dashed of 0 should be? It says that this is the limit as h tends to 0 of p of h minus p of 0 over h, which is the limit as h tends to 0 of well, actually, I'll just first of all I'll just say that this is equal to the limit. We know that this limit exists, so it's got to be equal to its right-hand limit. So all I've done from here to here is just put a little plus on the 0. So if this limit exists, it must be equal to the limit from the right as well. And this limit from the right here is equal to the limit as h tends to 0 from above of e to the 2h minus e to the 2 times 0 over h. Okay. Okay, so we've shown that this limit from the right here is equal to 2, and that's precisely what we wanted there. So I'll just write that in here now. Okay, so the left and the right hand limits agree. The left hand limit was 2 and the right hand limit was 2. And so that means that the limit exists and hence f is differentiable. Okay, so since the left and right hand limits exist and agree, the limit defining f dashed of 0 exists. Okay, hence f is differentiable at 0. Okay, which is what we wanted to prove. And of course, we weren't asked what the derivative actually was, but of course it's this number 2. Okay. All right, now I'd like to try and do this in with another method, method 2. And method 2 uses theorem 4.56 from the notes. Okay, and in that theorem, I won't write it out in full. You can have a look at the details. I'll tell you what it's about. But the theorem deals with a function of the form f of x is equal to p of x if x is greater than or equal to a, and q of x if x is less than a. And it says that this function is differentiable at a, provided it's got to be defined on an interval around a, and it's differentiable at a if it's continuous at a, and if the derivatives of p and q agree at a. So basically this says if f is continuous at a and p dashed of a is equal to q dashed of a, then f is differentiable at a. Okay, so we're going to use that theorem from the notes. Okay, now you can see that that we need to define p of x to be e to the 2x and q of x to be 2x plus 1, and this a is 0 in this case. Okay, so let's let p of x equal e to the 2x and q of x equal 2x plus 1. Okay, now we need to check that f is continuous. F is continuous at a. Maybe we'll check that first. So f is continuous at a means that the limit as x approaches a of f of x is equal to the actual value of the function f at a. Okay, so in this case a is 0. So what we need to check is that let's first of all, so we need to check the limit as x approaches 0 of f of x. Okay. All right. Well, in order to find the limit as x approaches 0 of f of x, maybe we should, it's defined differently to the left and the right. So let's calculate the left and the right hand limits separately first. So let's do the limit from the right. And f to the right, where x is greater than or equal to 0, is e to the 2x. That's the p of x. And this limit here is e to the 2 times 0 because the exponential function is continuous. So that's equal to e to the 0, which is 1. Okay, the limit from the left is equal to the limit from the left, and from the left for x less than 0, f of x is 2x plus 1. And this is a polynomial. It's continuous, and so we can just substitute in the value. So that's 2 times 0 plus 1 equals 1. So this is the same limit on both the left and the right, so they agree. Okay, so we can conclude that the limit as x tends to 0 is 1. And we can conclude it's 1 because the left and the right hand limits both said it was equal to 1. They agree and they say it's 1. Okay, now to be continuous, this limit should actually be equal to the value of the function at 0. So let's just work out what f of 0 is. F of 0, well, over here, if we put in 0, we get e to the 2 times 0. Which, of course, e to the 0 is 1. All right, so the limit as x tends to 0 of f of x is equal to f of 0. So that tells us that f is continuous at 0. So that's the first part we need for this to use this theorem. And really what we're saying here is the limit as you approach along this way is 1, and the limit as you approach along this way is 1. They agree, and so it's continuous. And they agree with the value of the function there, so it's continuous. Okay, we then just need to check, according to this theorem, that the derivatives of the two different functions agree at this point where they meet. So we need. So let's just calculate p dashed of x for this p of x e to the 2x. So that's 2 e to the 2x. That tells us that p dashed of 0 is 2 e to the 2 times 0, which is 2. And the other derivative, q dashed of x, is equal to, well, q of x is 2x plus 1, so q dashed of x is just a constant 2. Of course, if it's 2 everywhere, it's 2 at 0. Okay. So these two numbers agree. So let's just say, so f is continuous at 0, and for the p and q we've defined, p dashed of 0 is equal to q dashed of 0. So f is continuous at 0, and that is true. Hence, by the theorem, f is differentiable at 0. Okay. Now, one last little thing. You can see over here we didn't really talk about continuity at all, whereas over here we did. And on the picture it seems you certainly need continuity. Where has continuity come about in this? Well, the reason the continuity came into this is because up here, this, well, maybe I'll look at this one here first. This is the derivative from looking just at the function on the right. And you can see that this in this limit we've got here, we've got e to the 2h minus e to the 2 times 0. That's the same function there and there. But up here, we have the 2h plus 1, which comes from the definition of f here. But minus f of 0 came from the definition of that. And in order for this to be the derivative of the blue function, 2x plus 1, we need that this number here really does match what it ought to be for this function. So that's where the continuity comes in. This really has to be 2 times 0 plus 1 for this to work out. Okay, so both methods are essentially the same. This one here uses a theorem in the notes, and this one here uses the actual definition of differentiable.